I'm going to run you through fundamental calculus, at least one version of it for complex numbers. And that basically says, as long as you're in a simply connected region and you have a holomorphic function to begin with, you can find an antiderivative for this little f by defining big F to be the integral along any path from a fixed point, any smooth path from a fixed point, and that will be an antiderivative. So the first thing I'm going to do is prove that this makes sense. And the reason why there's a question is because if you look at, maybe here's your point z naught, and here's your point g, say, simply connected. If you want to figure out the value from big F of z, you have different options, right? I could take, if this is gamma, I'll get one value, I'll integrate, but I might also have another value, call it like gamma prime there. And I'm going to show you that regardless of the option you pick, you're going to get the same result. In particular, I can look at the integral over gamma minus gamma prime. So what does that look like? In purple, that's going to be the path that follows gamma, and then it goes the opposite way around gamma prime. So it goes that way and that way. And that purple should overlap the red and overlap the green perfectly, right, of f. Well, little f is holomorphic, so the integral around this closed curve has to be 0 by Cauchy's theorem. But we also know that we can split up this integral into, I don't know what that was, the integral over gamma and gamma prime. And so what I get is that the integral over gamma is equal to, since this subtraction equals 0, I get the integral over gamma equals the integral over gamma prime of f. And these were our two different possible ways of computing big F. So the takeaway is, it actually doesn't matter what smooth curve you use. Since f is holomorphic, it basically says that use any curve you like and you'll get the same value for big F. Okay, so let me pause here and I'm going to erase. So I just showed you that this function is properly defined. You can make sense of it. Now I'm going to show you that this value is actually, that big F prime is actually little f. And to do this, I'm going to let epsilon be bigger than 0, and I'm going to find a delta, which I'm not going to tell you about right now. For delta blank, we have, well, what do I need? I want the derivative to equal f prime, so the derivative looks something like this. If I take this quotient, all over delta, this is how I figure out the derivative. We take a limit, but instead, I'm going to show you that the difference between this quotient and f of z, what I want the derivative to be, this is roughly the derivative, it's an approximation, and this is what I want the limit to be. I'm going to show that this is less than epsilon for all delta z less than the real number delta. We're going to get this. So I'm going to work to prove that this is actually less than epsilon. And the first thing I'm going to do is I'm going to break this into another screencast. I've got about a minute left. I've learned my lesson. So here, stay tuned for part 2.